welcome you all. So today's lecture is for the stereochemistry of molecule with one or two or more chiral center. Then how their stereochemistry is being seen, and how does the stereo center or number of stereoisomer is calculated, how to check the either the molecule is having in a different stereo center. So in this topic we will discuss. If you see the overview of this overall discussion, so here we will see in case of a n chiral carbon, so here n could be like a chiral center, which could be 1, 2 or 3 chiral center. Then the compound will exit 2 raised to the power n optical active form. So here, by the simpler way, we will see how much optically active form is there. And for in case of a molecule, for example, if like suppose there are 2 chiral center, then there will be like 4 optical active form. So overall we will discuss here the chiral center which is having 1, 2 or more than 2 chiral or more than 1 chiral carbon here. Now if there are n chiral carbon, then to an optical active form will be seen from that particular chiral compound. And if like for example 2 bromo 3 hydroxy butane diacid, an example is taken here. So there are 2 chiral carbon number this and carbon number this. So there are, if you see the optical active form, so that is as per 2n rule. So 2n equal to, this is total 4 optically active forms will be seen here. So the 2 chiral carbon atoms of tartaric acid on the other hand, similarly you can see for the different other atoms or other molecules in a similar way. So they can be predicted by using the different forms. But here, like if you see their physical properties or properties of diastereomers, different diastereomers. So like in enantiomer, you already know these are having the different rotation with respect to the plane polarized light, as we all had discussion on that specific topics. So now the properties of, like in case of tartaric acid, which is the diastereomers. So specific rotation is having, for if you see the different rotations, and melting point for diastereomers, if you see these are also different in case of meso. Solubility is like same here. Other property, relative density, as we already discussed in the previous lecture about the different properties of stereomers and different forms of the stereomers. So therefore can be easily separated using techniques such as fractional. They can be separated out by different spectroscopic not you can say separation techniques, like chromatographic techniques. So different behaviors they show along with the plane polarized light. They have a similar but non-identical chemical properties. Particularly, they can react with chiral or achiral reagent at different rates. So also, they are represented different chiral centers. Here also, if you see, there are chiral center. This is also a chiral carbon. This is also a chiral. So more than one chiral center is there. So this is also designated like trio and erythro, and this is uh, different designations. Fisher projection can give them this kind of can form. So it is exist both like exist in staggered form, in which the bulky substituent are far apart as possible. So this minimize the energy in that case. The erythroisomer corresponds to the diastereomers, which when viewed along the bond connecting the chiral carbon, because these are the chiral carbon. Here we are talking about the connection with respect to these carbon. has rotational isomer in which all similar groups are eclipsed. So the diastereomer on the other hand does not have an isomer in which similar group are eclipsed. So we already discussed about the eclipsed form and staggered form. So staggered form means the bulky group will lie to each other, means apart from far away, so that there will be the least hindrance among them. So we already discussed in earlier lectures. So here you can say in case of meso compound, you all know in a case of meso compounds, like pair of enantiomer, this is the pair of enantiomer with once you will put the mirror image chiral center, you can see also they're having two similar chirality centers, such as all are optically inactive due to the presence of plane of symmetry. So all symmetry elements we have also discussed if there are even a chiral center, but if there are any plane which is passing or which is dissecting the molecule into same kind of fraction, like here you can see. So these kind of molecules is having plane of symmetry. So means one half of this can overlap on this half. So these forms are called mesoforms. So apart from only to check the chirality, you need to be recall the things which we had discussed in the previous lecture or earlier lecture about the symmetry elements. So symmetry elements is very important to see whether the molecule is having even a chiral center if they are having. So whether that is optically or they are having optically active or inactive. So that needs to be addressed when you check the molecule uh, with respect to their individual half on the same molecules. So even though you can check very easily, you can also know the priority rules. You can put the priority rules as we already have also discussion on that. So that will also helps to assign their designation, rectus or signature or anti-clock or clockwise direction. So by that way, and you can also check the molecules, either this is having a plane of symmetry or any kind of symmetry. If it is symmetry element is there, so then you have to designate or you have to say whether the molecule will be optically active or not. So this kind of question is very important with respect to once we observe the molecules and to check whether there is having certain kind of chiral center. So now coming to the prediction, how to predict the number of stereoisomers, like we said, one, two, or more chiral centers. So in that case, if having a more than one chiral center, then how can we predict or number of stereoisomer, or the number of optical isomer, or whether there are optically active or mesoforms, which is not as such optically active form, because if they are having a plane of symmetry, so obviously that is a mesoforms. So in case of mesoforms, if the molecule is having even a chiral center, so they will not rotate the plane polarized light, because that will be nullified. So here it depends upon the following: number of chirality center, how many chiral center is there, whether the chirality center are similar or dissimilar. We have to check it out in a molecules. For a molecule having dissimilar chiral centers, so number of optical isomer will be 2 raised to the power n. If it is a number of mesoforms, it will be 0. So if you will check the number of optical isomer, you have to use this. If the only in case for a molecule having dissimilar chiral center. For a molecule having similar chirality center, these molecules are of two types. Molecule having even number of chiral center, you have to see either 1, 2, 3, 4, how many number of, no, if it is we are talking like even, so then you have to see whether 2, 4, 6 like that. And if it is having odd number of chiral center like 1, 3, 5, 7 onwards, so this is very important to check it first. So this will help you to designate them. Uh, so for molecules having even number of chiral center, so then in that case, how you will calculate the number of optical isomer? The formula will be become 2n minus 1. So the number of mesoforms, if you want to calculate the mesoforms, then you have to use the formula 2 raised to the power n divided by 2 minus 1. So once if only you have to keep in mind if the molecule is having even chiral center, because now you know how to see the chirality or chiral center in a molecule. So once since we had already discussed how to see the chiral center, how to check the chiral center in a molecule. So one and only, if you don't know how to find out the chiral center, then even though by knowing this formula you will not be able to find out the you know have how many number of optical isomer is there, so you will not be able to find out it. So first foremost job here is in any molecule is to check that how much chiral center is there. So that is the first foremost priority. So after that, obviously, you will be able to find out the number of mesoforms at the same time. So number of mesoforms can be also find out. So this is the formula 2n by 2 minus 1, and here you have to keep in mind this 2n minus 1 formula for optical isomer, and for mesoforms in case of even is 2 raised to the power n upon 2 minus 1. And for if the molecule is having odd number of chiral center, so in that case the number of optical isomer will be 2n minus 1 and 2n minus 1 upon 2. So number of optical isomer will be from this to here. So the number of mesoforms here in this case 2n minus 1 are divided by 2. So here you have to divide it by 2. So once you will keep in mind these simple relations or simple relationship, how to calculate the number of optical isomer and number of mesoforms, then on that basis you can be easily find out the optical active form or optical isomer and mesoforms in the molecules. So this is very important for predicting the number of stereoisomer or number of the optical and mesoforms. So these all what we had seen can be seen from these examples, which is a very common example like butane 1,2,3 triol. So here now I'm not going to discuss already, since we had discussed how does this is the chiral center, this carbon, and there is like two chiral center is there. So first our for this molecule we have to watch the molecule, we have to see that whether there are the carbon is attached with four different kind of groups. So yes, of course here the carbon is having four different groups. So there are two chiral center is here. So now here the the chiral carbon, so n will be 2 dissimilar chiral carbon. So the number of optical isomer, it is very easy to calculate in such type of molecule. So it will be 2 raised to the power n. So 2n equal to 4 here, and number of mesoforms will be obviously as per the previous discussion, it will come as 0. So the student here you have to see how the total number of stereoisomer will be. You can calculate how many total stereoisomer, how much it will be, because first of all we have to calculate optically active isomer, optical isomer, and then we have to see mesoform. So the overall stereoisomer, how many is that? This is 4 plus 0 equal to 4. So you can see here also in these molecules 1, 2, 3, 4. So 3, 4 type of, this is the mesoform, obviously this is the mesoform. So the number of meso, this will not be the, you can say is not the optically active, and this is not the mesoform exactly, because this is the CH2OH group and this is CS3 group. So these are different groups, and here you can see in here two chiral carbon, this carbon and this carbon. So first and foremost, as I said, requirement is you all need to know how to find out the chiral center. So similarly, like in case of tartaric acid, here 1, 2, 3, First of all, you just see here also the chiral center is two chiral center has two similar chiral carbon atoms. So here has a two similar chiral carbon atom. Carbon chirality is there, but but the you can see chiral carbon atoms n equal to 2, number of optical isomer can be calculated here, and this is CHOH. Okay, this is CHOH. So with respect to this carbon you have to see, and with respect to this carbon, so number of optical isomer will be 2n minus 1, as we already discussed. 2 n equal to 2 minus 1 equal to 1. So the number of optical isomer will be 2. So these kind of small calculation you need to perform once the question has been asked to check how many optical isomer, mesoforms and stereoisomer is there in specific kind of the molecule if it is given in a problem. So you can easily solve out it by, if you know the basics, how to check it out. So number of mesoforms you can also find out for these kind of molecules. So this is the very simplest way as you can explain. And here the total number of stereoisomer can also be bigger. Now number of mesoisomer will come one form. So here the mesoforms you can also draw it by drawing the molecules, putting a mirror in between the in this molecule. Just put first it into in a Fisher projection. So projection formula and different projection representation we had already discussed in earlier lectures. So please recall all the lecture which we had discussed and delivered so far. So before coming to just this kind of problems to check, so then only you can find out this kind of solutions, or you can easily understand it. But if you don't know if you didn't listen the previous lecture, you will not be able to get how to find out this. So here you can see this. You had put the mirror over here. So this is a mirror image of each other, and you all already know if they are non-superimposable mirror image. If they forms once you are superimposing over here, so then that will be optically active here. And chirality, of course, is chirality is there. So two chiral center, as we said, if you can see if there is two chiral or no. This with respect to this carbon, this is the one species, this is the another one, this is the another group or atoms, or this is another one. But if you see in case of the mesoforms, so especially this one fragment can having the same part what you looks here. If you pass a plane over the middle of the two carbon carbon bond in single bonds, then you will can be dissect this molecule in equal halves, which if you remember previously we have had a also discussed, we cover this how to check it, the mesoforms, how to see the molecules, and how can we find out it. So the prediction is very important of the to visualization is very important once you are discussing about the stereochemistry. So in case of stereochemistry, the visualization of the molecule is very important. Without visualization, and by putting certain rules and the rules and the set of things which is being followed up to find out a certain stereomers or mesoforms or their optical active form. So then only you can be able to see, or you can be able to find out the exact answer. So here there are another example which is having right now. We had seen in previous lecture there in previous just slide we had seen the carbon or the molecule which is having two chiral center, but here we are can see there are 1 2 3, 3 chiral center. So look at here what happens when the molecule is having 3 chiral centers. So we know what is the formula and what is the relations to use or relationship we have to use for calculating optical active forms or optical isomer and meso and stereoisomer. So here if you say this is odd number of chiral carbon atom is in this molecule when we took trihydroxyglutaric acid. So in case of trihydroxyglutaric acid, so this is the simplest formula by which you can represent it in a Fischer projection, as you can see here in this molecule. It is represented over here. So either by using these equations, by using the simplest equation, you can calculate the isomer over there, and with this formula also you can find out the number of mesoforms and total number of stereoisomer, which is total number of stereoisomer will be the total number of mesoforms and optical active forms. So by either by doing this, you can check it out how many number of stereoisomer is there. So by putting this, again you have to put a mirror or imaginary mirror. You can imagine it once it suppose you are putting the molecule. So then how does it will looks like? Here it is looking like COOH, but exactly once you will draw it, this H will looks like towards this side. So this H will come this side, but for a simplest sake of representation, we in paper we had just put it here. And this H will be directed towards this end, OH is this end. So you all know this, how to represent it. And now you can also see here in this molecule, if you see if you pass a like this, if suppose you change the arrangement of the atoms, then you will see how does you know this is having a plane of symmetry. Again, if you see these kind of molecules, so you all must have a prior knowledge or prior idea about the different symmetry elements. So here one plane can be passed which dissect the molecule into equal halves. So just see the one portion which is similar to the another one. So this portion, this third representation of the molecules is also having a plane of symmetry. Now you can change the position of this OH with respect to this hydrogen. So you will see again there is a one plane can be passed. So by this way you can see this is also having a plane of symmetry. So if the chiral center is more than 2, then how we can calculate the optical isomer, mesoforms and stereoisomer can be calculated. So these overall practice represent that by applying the simplest approach, we can calculate the number of total number of stereoisomer, or another way is calculating this is by drawing the their actual structure and then visualizing the molecules with respect to putting a like a mirror image, and by watching whether there is a plane of symmetry or not. So by that way also we can see, but this is a time taking process. You have to draw all the structure, you have to just imagine, you have to just check it out whether this is happening or not. But if you know the simplest approach or rule which is being assigned for calculating the chiral center and how many chiral center and how does we can check the optical isomer, mesoforms and the stereoisomer and all these rules, if you know for each and every, like even in case of even chiral center if it is there, or if it in case of odd number of chiral carbon is there, then you can easily find out the total number of stereoisomer. Mesoforms you can also check with this same approach. and optical isomer you can also check with the same approach. So this is what we had discussed is very important here. And now if you see from the overall discussion, as per the today's lecture discussion, we discuss a chiral center which is having more than one chiral center, or we also check how much optically active form is there, how many mesoform is there, and how to calculate the total, the total number of stereoisomer. So since that is very important, as far as calculation of this, so either you can draw it with the help of different structural way. So if you see the overall discussion, we discussed today the compounds with several chiral center, how to check their different forms, their different optical forms, their different whether they are optically active or not, whether they are having a mesoforms like we seen in where the plane of symmetry is there, prediction of stereoisomer already, number of optical isomer and mesoforms we had checked, and we check with in a very different kind of examples like multiple chiral centers. And on the basis of multiple chiral centers, you can check the optically active forms and inactive form, or you can say the mesoforms, and you can also check with addition of the both, you can see how many stereoisomer is there. So these kind of overall discussion can makes a, the various kind of questions can be asked, like with giving a specific kind of molecules, and it can be asked calculate the number of optically active forms or optical isomer, and how many mesoform is there, and if it is asked how many total stereoisomers, so you have to also see the same approach and you can calculate it out. Mm, Now here these are the some of the references and resource material from where it has been taken up. So this all material is only for the instructional purpose and instructional material, and having no intention for any of the commercial use. So here Halil books you can also refer, which is also very good for that. And now I thanks for all for watching this videos and listening this video lecture. Thank you so much.